All right, so now we're going to talk about the Legendre transform, which is a way of expressing duality between convex functions. It's like and things along those lines. Okay, so the Legendre transform. So let's say we're given a convex function. Okay, and then we'll consider the following. So we're going to look at the gradient of that convex function at a particular point. And I'm going to denote that by because C star is equal to the gradient of the convex function at the point C. Okay, so this is just the normal vector, right? To the supporting tangent hyperplane. To the convex function at the point C. All right, so imagine a picture like this. All right, and there is a tangent hyperplane, and this is the normal, right? Okay. So, all right. So the bottom line, if you will, is that because of the fact that the function is convex, it turns out that there is a one-to-one correspondence between the point which you're evaluating the convex function at and its normal, right? So if you imagine looking at the normal, it's like to this convex function at different points, you'll see that it sweeps out different values basically. So there are basically no 2 points on. It's like in this direction. It's like where the normal is the same. Okay. So you can observe that the normal okay is well, more precisely, that the map from the point C to C star, right, is 1-to-1 and differentiable. Okay. All right. So because of the fact that it's one-to-one differentiable, you can imagine that this transformation gives you a change of coordinates. Okay, so we can view this as a change of coordinates. Okay, and then this transformation is called the Legendre transform. So basically, given a convex function, right, you can construct a different coordinate system. It's like which is in some appropriate sense dual, and that duality is defined by this convex function, if you will. Okay, so that's one observation. So the natural question to ask then, right? So you have a map from C to C star, which can be viewed as being related to the gradient of a convex function. You can ask naturally whether the map from C star to C can be similarly expressed as the gradient of some other function, right? So, so the map C to C star, right, is given by C star is the gradient of a convex function at C, right? So the question, natural question asked is, does there exist some dual, if you will, to the convex function such that C is equal to the gradient of this dual C star, right? All right, so let's see how you can do this. Okay, so consider the following. Which is given by C dot C star minus psi of C. All right, so this is also a Legendre transform, okay, where you Legendre transform the convex function, okay? And if you, it's like if you know something about mechanics, it's like then what you can observe is that, for example, if you had a Lagrangian, right, then the momentum is given by the derivative of the Lagrangian with respect to the velocities, right? So there's this duality between the velocity variable and the momentum variable. And then it's like, again, it's like in the context of Lagrangian mechanics, if you have a Lagrangian as your function, then you can construct the Legendre transform with the Lagrangian, which would then be something like P times V, or P times Q dot minus the Lagrangian. That gives you the Hamiltonian, right? So yeah, so this Legendre transform of convex functions, right, it's also exactly the relationship you have. It's like between Lagrangians and Hamiltonians on one hand, and the relationship between C and C star is exactly the relationship you have. It's like between the say the position velocity representation versus the position momentum representation. Okay, so the point basically is that it's like we're referring to this as Legendre transform. It's like, and if you've seen Legendre transforms in the context of mechanics, right, you see that as changes of coordinates on the one hand, as well as changes of, say, from the Lagrangian to the Hamiltonian. Okay, all right. So anyway, so let's consider this this thing. It's like with the proviso, right, that it's like the two variables C and C star are related by the Legendre transform. Okay, and again, it's like if you're putting your mechanics hat on, this is exactly how you would define the Hamiltonian in terms of the Lagrangian after the suitable identifications, which we referred to before. Okay, all right, so, okay, so if you differentiate, so if we differentiate this equation, with respect to C star, right, we have that the gradient of C star, sorry, at psi star C star, right, is equal to C plus d C star, right, minus the gradient d C star. All right. So that's just the that just comes from thinking of this constraint as saying that cos c is equal to some function of cos c star, which is essentially the inverse of this relationship. Okay, all right. So so we've differentiated that, and let's see what happens. So we know that cos c star is equal to the gradient of cos c psi cos c, and all right. So by this relationship, right, this term here is cos c star. So those two terms are equal to each other, so they cancel out. So you're left with the gradient of psi star cos c star is equal to cos c, right? Since we have this relationship, the last two terms cancel, and we are left with the fact that the gradient of psi star cos c star is equal to cos c. Okay, all right. So now we have this kind of nice duality where on the one hand cos c star is equal to the gradient of psi cos c, right? And cos c is equal to the gradient of psi star cos c star, right? So that's what we had set out to try to do, right? We wanted some notion of a dual, it's like of the convex function, whose Legendre transform gives you that inverse map between cos c and cos c star. Okay, all right. So psi star is the Legendre dual of psi. And you can also check that instead of looking at this restriction, right, so you can observe that you can always say that psi star cos c star is equal to cos c dot cos c star minus psi cos c, and then I extremize this over cos c, right? So another way to sort of think about this is that, you know, inside the parentheses you have something which depends on cos c and cos c star, all right? But the left-hand side, it's like has a function which only depends on cos c star. So the way you sort of get rid of the dependence on cos c is to extremize over it, okay? And it's easy to see that this is equivalent to this other definition because the stationarity condition for this extremization is nothing more than cos c star is equal to the gradient of psi at cos c, right? So because if you just differentiated this thing with respect to cos c and set it to 0, you get exactly this condition here. Okay, so it's easy to convince yourself that this is equal to okay, all right. So why is this former approach sometimes preferable? So this is preferable in some sense because, you know, sometimes there's degeneracy. It's like if you break the assumption that psi is convex, right, or strictly convex. So if you break that assumption, it's like then what happens is that the Legendre transform is not invertible, okay? And if the Legendre transform is not invertible, it's like then having this condition here is kind of a harder thing to work with. Whereas if you use this extremization, it's like way of expressing the Legendre dual, it's like that still makes sense, even if the Legendre transform is not invertible. Okay. All right. Anyway, so and then it's like one other thing it's like you might want to do. It's like if you really wanted to nail everything down, is to make sure that this Legendre dual of a convex function is again convex. Okay, so want to check that psi star is convex. Okay, and the basic idea is that so you can check that the Hessian of psi star, right, is given as follows. So G star plus C star is equal to this. This turns out to be the Jacobian of this change of variables. Of the inverse transform from C star to C, which is the inverse of the Hessian of the original convex function. Okay. But you know that that Hessian, sorry, the Jacobian of that convex function, sorry, what am I saying? It's the inverse of the Hessian of the convex function. Okay, yeah. All right, so the Hessian, it's like of this convex function is positive definite, okay? And so basically what happens then is that the inverse of that Hessian will also be positive definite. Okay, so the Jacobian is also positive definite. Since it is the inverse of a positive definite matrix. Okay, all right. And that means that this psi star is convex. Okay, all right. So that's kind of interesting, right? So it's not the entire picture, right? Because now it's like we have with the Legendre transform this duality. It's like between one coordinate system and a different coordinate system, and with duality between one convex function and another convex function. Okay, and of course, you know, it's like leading up to this, we were talking about Bregman divergences, which are ways of measuring distances between 2 points on some manifold, right, with respect to some coordinate system typically. And this notion of a pseudo distance basically was derived from some sort of convex function. So how, you know, do you sort of contextualize what we already learned so far into the setting then of Bregman divergences? So let's see what's happening. All right, so imagine you have 2 points. It's like cos C and cos C prime, right? Then with this Legendre transform, we can look at cos C star and cos C star prime. Okay, and then we have this notion of a Bregman divergence between these 2 points, right? And the Bregman divergence with respect to a convex function. Oops. Okay, so the natural question to ask is there some sort of relationship between something like this and something like this, where I've dualized everything, right? So that's the question. Is there some sort of relationship like that? Okay, so let's see what's happening, right? So the point is that a new Bregman divergence can be derived from the dual convex function. Okay, so let's see what happens, right? So we have d psi star of cos C star to cos C star prime. Okay, and this is defined to be nothing more than psi star at cos C star minus psi star at cos C star prime minus the gradient of psi star cos C star prime multiplied into cos C star minus cos C star prime. Okay, so this is what we call the dual divergence. Okay, so what happens is that you can check that this thing okay, is equal to the divergence, the primal divergence, for lack of a better term, okay, of the 2 points, all right, corresponding to the dual of this, but where the entries are reversed, right? Because here we have the non-prime, then the prime thing, here with the prime, then the non-prime thing. So they're equal, except that we have this interchange. So this relationship doesn't hold. It only holds if you sort of reverse the order when you go via duality. Okay? So you can check this. This is true. Okay. And you know, as you might expect, it's like the way you do this is by just using the definition, it's like of the Legendre dual, it's like of the convex function, as well as the Legendre transforms, which relate everything together. Okay? So when you have something like this, it, you know, the Bregman divergence, it's like in this way, which is somehow a little bit more reflective, if you will, of the equal footing. It's like of the two quantities, if you will, more equal footing, right? You might ask whether or not one can rewrite these Bregman divergences in a way which reflects the fact that, or what one might expect, that there's some sort of relationship between, or I mean, how should I say this? But yeah, the Bregman divergence, it's like can be expressed. It's like in terms of both the convex function and its convex dual. Okay, so let me state the following theorem. So the theorem is as follows, right? So that the Bregman divergence between 2 points P and Q can be written, it's like as the convex function evaluated at the coordinate associated with P plus the dual convex function of the coordinate associated with Q minus cos Cp dot cos Cq star. Okay? Right, so where cos Cp is the coordinates of P in one coordinate system, and cos Cq star, right, is the coordinates of Q in this dual Legendre transform coordinate system. Okay. Right. And of course, so how do you go about proving this, right? So the proof is, so let me just sort of sketch it, right? So you can check that this dual convex function is equal to cos Cq dot cos Cq star minus psi cos Cq, right? And then you substitute this into this relationship. So substituting this into sort of that equation, and using the fact that the gradient of psi cos Cq is equal to cos Cq star gives the theorem. Okay, all right. So anyway, and in any case, it's like the important point, if you will, is that if you have this particular characterization then of the Bregman divergence, it's like in terms of the convex function and its dual, right, as well as the Legendre transform related, it's like coordinates, right, then it's like statements like this, it's like are sort of much easier to prove, basically. Okay, all right. So let me just stop here for now. It's like in the next thing we'll talk about our sort of this idea of affine, it's like, and dual affine coordinate systems, it's like, and the various notions of connections and parallel transport. Okay, so let me just stop here for now. Thank you.